Welcome to today's webinar, which is more informed slope stability analysis with LimitState GEO. I'm Tom Pritchard. I'll be introducing you shortly to our speaker for today, who is Dr. Colin Smith. During the webinar, we'll demonstrate how you can use LimitState GEO to help get more from your geotechnical analysis. So you'll see how you can identify a wide range of failure modes using the software, how you can incorporate a range of geotechnical features, and also find out how to conduct what-if type analysis to quickly gain a better understanding of the problem that you're working with. The main section of the webinar is going to run for approximately 40 minutes, and this will be followed by about 5 minutes at the end for questions. You can post these at any time using the question panel that should be present in the webinar interface in front of you. We'll try to answer as many of the questions as we can in the time available, but it's not always possible to do this. I do apologise in advance if we're unable to get to yours, but we will, after the session is finished, try to answer everything via email individually. So without further ado, I'd like to pass you over to our speaker today, who is Dr. Colin Smith.
Thank you, Tom. So good afternoon to those of you in the European time zone, morning or evening to those of you joining us from elsewhere in the world. So as mentioned, my aim today is to show you how you can get more from your slope stability analysis with LimitState GEO. So to this end, I'll be primarily using the software directly to illustrate key points, but I'll make use of a few slides at the beginning and end for introduction and summary. And we'll be looking at two specific issues: non-standard slope failure modes and the what-if type analyses, which will encompass addition of other geotechnical features. As this is a problem-specific webinar, I'll focus on how to use the software to solve slope stability problems, and so may therefore skip over some of the details of how to use the software. But the process should hopefully be clear. That gives us the overview of what I'm going to talk about today. So we'll kick off saying a little bit about the LimitState company itself. So University of Sheffield has been conducting research into LimitState analysis and design and the use of optimization in civil engineering for almost 2 decades now. The company LimitState was spun out of the university in 2006 with the aim of making this research available to industry and providing easy-to-use, powerful software tools that are well validated and supported. The company has 4 products at present: LimitState Ring, LimitState GEO and LimitState Slab, and not on this slide another product called LimitState Form, which is optimized structural and mechanical design. And these software packages are used by both consultants and contractors, large and small, in over 30 countries worldwide. Now, as you're probably aware, LimitState GEO is a general-purpose ultimate limit state software able to determine the collapse state for any problem geometry, and it's able to model slopes, retaining walls, structural elements, and soil reinforcement as shown in some of these examples. So our aim is to focus on slope stability analysis today. So just a sort of quick recap on standard methods. We look at standard textbooks. There are a number of conventional methods. We'll look at 3 of those. So the simplest is probably translational slip. This really only applies to infinite slopes, but it's straightforward. And the factor of safety in this type of calculation is effectively defined in terms as a factor on the soil strength. Taylor method is technically an upper bound limit analysis approach, and it looks at slip circle mechanisms in undrained soils, and the calculation process again generally determines a factor of safety as a factor of safety on strength in that particular analysis. It's not necessarily optimal, but is usually very close. The more general purpose approach, the method of slices, this is a limit equilibrium approach. So here we have to make assumptions about the shape of the slip surface, which in many cases will be chosen to be circular, and where it is. And it's not necessary that that slip circle is kinematically compatible in a limit equilibrium analysis. Generally, the problem isn't statically determinate, so we have to make a number of assumptions about interslice forces in order to come up with a solution. though these slices that are indicated in the diagram don't necessarily slide relative to each other. And again, for this type of calculation, we can define the factor of safety that we get out of it essentially as a factor on the soil strength measured over the slip surface. And this is probably the most popular slope stability analysis method, and it was essentially developed to facilitate analysis by hand, but is now automated and forms a significant type of geotechnical software. Now, if we look at geotechnical analysis software that's available, then we have those, such as slip circle analysis, that are based on conventional approaches and do a pretty good job specifically for particular problems such as slopes. And on this diagram on the bottom right, we have, for more complicated analyses, finite element software, which we can pretty well model any problem geometry, and we can model a range of complex soil behaviors. But typically we require a lot more expertise to use that sort of software and a lot more data for the soil. And filling the gap in between, we feel is computational limit analysis or rigid plastic analysis. And this kind of method gives you the flexibility of finite elements in terms of being able to model and solve any geometrical problem, but gives you the ease and use and simplicity of traditional methods. It's a ULS method, but essentially all you need are cohesion of the soil, the friction angle, and the unit weight. And such a method can be used to solve masonry arch bridge stability problems in our product limit state ring and concrete slab yield line problems as well. So just a quick background to limit analysis. I've mentioned the word a few times before. For those of you not familiar with the actual rigorous definition, it relies on a rigid plastic assumption of material behavior. So it's not a method that allows you to define deformations, but it's very good at determining ultimate limit states at collapse, and that's what generally you're interested in slope stability. And there are two well-known theorems that can be used in limit analysis, lower bound and the upper bound. So the lower bound method finds a state of stress in equilibrium that nowhere violates yield, and the upper bound finds a compatible mechanism of collapse and determines the collapse load through a work equation. And the optimal solution of either method is the exact plastic solution. In limit equilibrium, generally some of these conditions are relaxed, such as not requiring kinematic compatibility or equilibrium everywhere. Now, the LimitState GEO software is an upper bound method, but due to its formulation, it's very good at finding the near optimal collapse mechanisms. And no assumptions are required in the method except plasticity theory. For slopes, we're normally interested in a factor of safety on strength, as I mentioned earlier on. All common slope methods calculate this. So from now on, I'll refer to our factor of safety as a factor on strength. The example we've shown here in the animation shows a failure mechanism that is neither planar nor circular, and it's generally following lines of weakness in the soil. And the software is able to find the critical collapse mechanism. It makes no assumptions about slip circles, shape of slip surface, etc. So how does this method work? Well, the key enabling technology is what is called discontinuity layout optimization, which is a rapid and direct means of analyzing the collapse state. It was the outcome of a EPSIRC-funded research project at the University of Sheffield, and the key publication that underpins its working came out in 2007 in the Proceedings of the Royal Society. And the way it's formulated is that it converts that collapse problem into a simple linear optimization problem, and I'll try and explain that in very simple terms. So here we have a very simple problem. Essentially we've got a rectangular block of soil with fixed boundaries to the left and to the base, and a surface load over part of it. In this method, what we do is, instead of using elements like a finite element approach, we populate the domain with nodes. So here I've just put in 12 nodes. And then what we do is we connect every node to every other node with a hypothetical slip line. So here we've got 12 nodes. The number of hypothetical slip lines are 12 times 11 over 2, so there's 66 possible slip lines. And then we can feed all of those effectively into a linear optimizing solver, and it will pick out the critical mechanism that dissipates the least energy for that, built from those potential slip lines. So here we have the mechanism. Just 6 of those 66 slip lines form that mechanism, and that is the one, for that level is this discretization, that is the critical mechanism that dissipates the least energy. Now, we've only used 12 nodes in this problem. Normally we're using thousands of nodes, or hundreds of, or thousands of nodes, and so we get a much more accurate result, and generally the accuracy is going to increase with the number of nodes that are used. Okay, so I think that's explain the DLO. So just to summarize, it's a simple linear optimization problem which is easy to solve. With modern linear programming solvers, they're capable of solving problems of thousands, if not millions, of variables very rapidly in modern computers. When the software has finished finding the critical collapse mechanism, as in this 2-layer slope problem, it connects the slip lines together and actually finds the elements in order that it can animate those and to aid interpretation, so you can see how the failure mechanism is evolving. And this animation, it's strictly only valid at the instant it starts to move, but we take it further than that so you can see what's going on. And it basically gives you velocities of movement, but it cannot be used to determine displacements. Okay, so I think that is enough introduction. As I said earlier, increasing number of nodes used will allow more potential slip lines and a more precise mechanism to be identified. As with any numerical software, you obviously would want to be sure that it's doing the right thing and is giving you accurate answers. So every time the software is modified, we run thousands of tests automatically on the software to make sure it still does the right thing. A lot of these tests are based on solutions that have known solutions to particular problems in the literature, and we've put around 100 of these up on our website to show you the comparison. So here is a very simple slope stability problem, fairly steep angle in an undrained soil, and on the website you can find that the benchmark result in the literature is 5.25. The software with not that many nodes gives you 5.35, so it's out by 2%. And there are generally, you find that most of the results the software gets are within just a few percent of the known result in the literature. One other little verification here. So we talked about the Taylor stability charts earlier on. So here again, we've just done a few simulations with the software and show that we get very close to the Taylor results. So the lines are the original Taylor theory. The points on the graph are those generated by the software. And you'll also find on the website quite a lot of bibliography, so a lot of increasing number of journal papers, scientific journal papers being published on the using this software, and you can download that from our website to see the sort of data results that are being got and the comparisons that have been made. So that is available to download and lists a whole range of different applications. I've just picked out the one here on slope stability. Okay, so that's enough introduction. We'll start out illustrate the software now. So I'm just going to bring up the software. Okay. So when I start the software, this is the standard layout. You'll see a number of buttons along the top, along the left-hand side, and various windows. And I'll describe these as we go along. So to start a new project, we just click New. So I could click this button, New, or File, New, and we get a choice of Quick Create. So we can create an empty project, which means we just draw our own geometry, and we can put in any geometry we like, or we can use the Quick Build wizards, which create standard geometries, which we can then modify later. So we'll start with a slope, which is that one. Click OK. You can put some background information about the project or the analysis here. We can then put in a geometry for the slope, so I'll stick with the defaults in this case. If we want to put in a water table, we can put that in, stick with the defaults again. We can then define soil properties in this case, so we give the soil a color. We can put in an undrained shear strength, a unit weight, which is effectively the unit weight above the water table, unit weight below the water table, and we have a choice of whether the material we're defining is behaving in an always drained manner or an always undrained manner, or a mix of or a choice between the two, and we can set a global setting for the problem to say whether it's a long-term or a short-term analysis. If it's a long-term analysis, then the software will pick the drain parameters. If it's a short-term analysis, it will pick the undrained. If we just selected always undrained, then regardless of whether it's long or short-term, it will always be treated as an undrained. So we'll stick with that. We can apply surcharge in this wizard. We'll leave that at 0, and we can decide how many scenarios. So it's possible to actually use a number of different partial factoring approaches. We'll look at that a bit later, but here we're just going to stick with unit factoring everywhere. And then finally, we have a choice of analysis. So we can ask the software two questions essentially. What load do we have to increase in the problem to cause collapse, or by what factor must we reduce the strength of the soil to cause collapse? For slope stability, we're generally interested in a factor on strength, so we're going to stick with factor on strength. And we have a nodal density here, so this is a number of nodes that we're going to use in the problem. So as I said earlier, the more nodes we use, the more accurate we get. But what I will do here is I'm going to use a coarse nodal density just to speed things up, and I click finish and it draws my problem. So this is a very steep undrained slope, typical sort of example as analyzed by Taylor, and all I have to do is click solve. So I click this button up here and it rapidly finds the failure mechanism. So that's a slip surface that passes through the toe, and I get an adequacy on strength here. So that basically means what I have to factor the strength down. And if I click on this here, it tells me what that means in detail. So it means that for soil A, the specified value is 50. After partial factors are applied, unit factors are applied, we have 50. But the value actually required for collapse is 20.18, and that's a 50 divided by the 2.47. And so we can treat that adequacy factor really as a factor of safety on strength. So just to be clear, that the strength had to be reduced by roughly 2.5 to cause collapse, so I can change the property just to illustrate that. So if I click anywhere, anything I click on the screen, its properties appear in the property editor on the right. So I click on this block, it gets highlighted, and its geometry gets displayed, the geometry editor down here, and various details to do with the nodal spacing and so on, and materials within it. I clicked here, and it says it's a material soil A. I can click on here and see the properties of soil A, or I can look in what we call the Materials Explorer here on the left and simply click on soil A, and its properties appear here. So recall we gave it an undrained strength of 50. If I reduce that by a factor of roughly 2.5 down to 20, then we would expect that this slope is just on the point of failure. There is no margin of safety. So if I click solve again, then we get 1 roughly, which is what we're hoping to get. So it's very easy to do what-if type calculations, or to try out different changes. So I can modify the slope angle, get a different mechanism. So for example here, I can move that, I'll move that back a wee bit, make it a bit shallower, and then resolve. Then I get a different mechanism, and here you can see now that the slip surface is going slightly below the level of the toe and up. The problem with this analysis is, one thing to watch out for is if these boundaries, so this one on the left, is not a real boundary, it's just an artificial boundary. Unless there's really rigid rock there, this is not going to happen, and this mechanism is actually intersecting the boundary, so it's not fully accurate. So really I should move that boundary sideways. I can do that in various ways. I just click this ortho button, it forces this changes to the geometry to be orthogonal, or horizontal or vertical. I just drag that sideways and then reanalyze. And it's now got more freedom. It's got a bigger space to find the mechanism, so the collapse factor of safety goes down, but it's still intersecting the boundaries. And in fact, I'm onto a losing game here. No matter how far I put the boundaries out, the mechanism would still touch the boundaries, because for this very special case, the critical mechanism is actually a slip circle of infinite radius. Now, I've been using a coarse grid of nodes for speed here, so if I go preview nodes, you can see the number of nodes I'm using, and it's building the collapse mechanism out of a whole set of slip lines that are connecting every node to every other node. I can increase that to medium, and again I've got more nodes in there, so if I click solve I will get a slightly more accurate answer. It's gone down from 1.09 to 1.08. Get a different mechanism, takes a little longer to solve, and if I go to fine, again I've got more nodes, and again it takes a little longer to solve. Generally I would recommend working on coarse and medium if you're doing what-if type calculations, trying to get a feel for the problem, and then when you want to refine down to getting the actual answer for your final design, then going to refine a very fine number of nodes. So I'll just revert that back to medium. And last thing I'm going to do is put a layer of very soft clay at the base of the slope. So if I can add things to geometry. So this is me adding a line, so I'm going to link up the line there to there, and then the materials we have here, there are some built-in materials with a little lock, so these are just for initial sort of doing what-if calculations to give you rough general properties of soils. The specific values don't have any particular formal meaning, but it gives you an opportunity to use those, but you can set up materials of any properties that you like. So I'm going to put a layer of very soft clay at the base of this slope. I'm going to replace the original material. So if I do another analysis here, then we get a slightly different mechanism and a lower safety factor. And if I drag these boundaries back again, hopefully we don't get a significantly different mechanism, so that point of intersection up there is about right. Now we could look at a few other examples, but in view of the time, I'm just going to, rather than using the software, look at a few pre-solved problems. So we're going to look at some layered strata and a reinforced embankment. So I'm going to jump back to the PowerPoint. Okay. So here's a pre-solved example. So it's a slope failure on a layered strata with a retaining wall and a water table. So we have some strong material down here. We have a weak stratum separating it and the surface deposits. And here we've got a retaining wall constructed and some backfill behind it. And you can see that the slip mechanism starts up at this corner, joins a weak interface stratum, dives under the retaining wall, and then comes up again. So again, it's not following any slip circle or any predefined line, it just finds the optimal slip mechanism. We can also look at failure mechanisms of reinforced embankment over soft soil. So here we have simple failure of the embankment above the reinforcement in the base layer, if the base layer is strong enough. You can also, if the base layer is soft and weak, then you can get a deep-seated global failure. If it's very soft, then you can just find the whole embankment effectively sinks downwards and extrudes the clay sideways, a kind of extrusion problem. Or you can get a similar mechanism, a bit of a mix of the second and third mechanisms, where you get a bit of extrusion and the reinforcement bending effectively at those points. So we can model reinforcement in there. So we'll do some examples then, some what-if analyses. So we've got a problem here. Of a 10-meter high slope, 20 meters long, and a soil C-5, 5-30, unit weight of 20. If you do a Bishop simplified method, you get a factor and strength of 1.6, but you do need to make some assumptions of interlaced forces, and generally, often you need to specify entry-exit points and centers of rotation. So we'll pull that one up on the software. So we say no to that. And we're going to look at this one. Okay, so that's the geometry setup. If I click on here, we can see the soil. So it's got a strength of 530. And if I click solve, very quickly finds the mechanism, and we get an adequacy factor, a factor strength of 1.63. So that's very close to the slip circle method, a slices method. But there's no need for assumptions of interslice forces or entry-exit points. That just comes out as the optimal failure mode. Now, we can model water here by various means. I'll only look at a very simple model given the time available of a simple phreatic surface. So I'm going to draw in a water table near the surface. So I can draw in, I'll just turn off this ortho button, which will stop it wanting to go horizontally or vertically. So I can draw that in, finish. So we now have a water table near the surface. And if I solve that, taking a little longer to solve, but comes out with a adequacy factor of 1.21. So again, as we'd expect, presence of water is reducing the margin of safety on that slope stability. I shall clear the water table, and we can also model things like pre-existing slip surfaces on thin layers. So, for example, if I had a pre-existing surface which ran from here, say, back to there, and I'll make that to have the strength of a soft clay, so we could put any property we like on that, but that's a much weaker one. If I click this button, I can add a vertex. If I wanted this slightly curved, I could lower it down. I could add more vertices and make it more curved if I wished. But if we have that sort of solution, then again, the software will seek out the most critical mechanisms. If I click solve on that, you can see that it's finding a mechanism that basically involves sliding down that slip surface and using quite a lot of it in order to give me a lower strength. So we're now down at 1.17. So it's just gone down slightly, sorry, it's gone down from the original 1.63. So adding in that weaker material has definitely given us a lower factor of safety, and the software will just search out the critical mechanism and find that particular slip surface. If we want to, actually, sorry, at that point I meant to show you the report, so we get the analysis for that. Once you've got an analysis that you're satisfied you've got it set up correctly, you can generate a report. So here we have analysis report. You can include various items in that, but we'll just click OK. So essentially the report gives you a bit of background about the method of analysis, a summary of the problem, the parameters employed in the problem, an example of the failure mechanism, and if you want it can give you all the background geometry, material properties, partial factors used, and so on. So, and that can be that comes out as an RTF file, so it can be incorporated or edited into documents. If I click on the undo button here, we can remove previous things, so I'll get rid of that weak surface. As I said, it's very easy to play around with the geometry. So what happens if I wanted to put a slope in the middle of this, in the middle of the I'll throw a load in the middle of the slope. So what I'll do here is I'm just going to put in 3 vertices, drag that one down a bit, stick that one across. Like that, and I can put loads on the surface here. I'm going to put a permanent load of value 40 kPa on that surface. So we have a load there, and I can see whether that affects the stability of the problem. In this case, you can see that it's actually identifying that the lower slope will fail first under that load, with that applied load. Had I made this load a little bit lower, I can drag that down to there. You can see that the software then says, you've got a very steep slope behind that load, we're going to get a local failure at that point, and that's more likely to fail. So again, it will find the critical mechanism in those cases. Let's just revert those, get rid of those. So again, if you've got a slope problem and you're looking at slope improvement, so you want to try and increase the stability, the various options, you could regauge the slope, or for example, you could add a berm at the base of the slope. So if we just look at what the failure mechanism for this is, basically coming out above the toe, but I could draw in. So I use this polygon tool here, start at this point, just say, well, what happens if I added a block of soil here, just make that slightly less steep, and I'll put in a dense sand there and solve that. So we had a 1.63 with the factor of safety. You can see that the presence of that berm has forced the mechanism to come out above the top of the berm, and I've increased my safety margin marginally. I've gone up from 1.63 to 1.7. I could change the size of the berm and experiment with the changes in that. So we undo that and revert back to where we were. We could add a retaining wall to that slope. I haven't got time to go through that in this presentation. Final thing is slope reinforcement. Really describing how we model reinforcement is beyond the scope of this presentation, but I'll show you the addition of one soil nail halfway up the slope. So what we do is we can draw in a boundary in the position where we want to have the nail, and I put in a little vertex as to where I want the length of it to go to say there. And then I'm going to use a soil nail. There's a built-in soil nail material here. I'm actually going to duplicate that material so I can then change its properties. It appears up here. Drag and drop that onto there. I've now got a soil nail. As I said, I haven't got time to explain all these properties, but these properties basically give you the interaction coefficients between the nail and the soil. So I'll put those in as such. I want that to be 0. And then we solve the problem. And what we'll find is that that one nail is going to have a slight increase. So again, we've improved the capacity. It was 1.63, it's gone up to 1.74. And what effectively the soil is shearing past the nail is staying where it is. And so we're getting some improvement. If we were to reduce the length of the nail, so it's short and rather not really doing anything, again, if we do the analysis, you find that then the software says, okay, I'll just put the failure mechanism around the nail, and that nail is then providing not a lot of gain. We've just got up from 1.63 to 1.65. So again, as you can see, the software is finding the critical mechanism. Okay, well, we're now coming towards the end of the time period allocated for this webinar, so I'm just going to wrap up with some conclusions. So hopefully you could see that the discontinuity layout optimization method, it's as straightforward as using the conventional method of slices, but with the added advantage that you don't need to specify entry-exit points, a solution method, interslice, shear normal, force functions, or a search space. And the method automatically will search all possible failure modes every time you solve, so it's able to find the critical slip surface even if it's highly non-circular or localized. Hopefully you've seen the workflow is straightforward. It's very easy to put in the geometry, change geometries and report. So you're in control. You can solve with one mouse click, and it's very easy to add partial factors. So a lot of our customers use the software to answer what-if type questions, experimenting with different changes in geometry or adding stabilizing elements to see what works best. So it gives you an ability to get a better feel for the problem. As you see, software solves generally in a few seconds, so you can pretty well use it interactively. And one piece of software can solve any ULS problem type, so you don't need to put in any idealization or correction factors for non-standard geometries. Don't need to learn how to use many different programs. The the software will solve foundation problems, retaining walls, other problem types as well as slopes. Okay, so that wraps up the presentation. So apologies that we started slightly late, but we have some time for questions. So if there are any questions, I will answer them. So I've got a couple of questions here. Is the deformed shape derived by the software accurate enough to use to determine where to install monitoring equipment? So that's a good and interesting question. I think the deformation pattern is going to show you the general areas where you're going to get failure and shearing. Clearly the software is it's using an idealized model of the soil. I guess I'm not entirely sure. It depends what sort of monitoring equipment you're installing, but if you're looking for say deformation or inclinometers and so on, all I could say is it's going to give you a very good indication. It is an idealization, and you will get you'll obviously get some deformations outside those plastic zones because we are analyzing the plastic limit state in those cases. Because of frictional soils, plasticity, the theory of plasticity that's employed in the software employs an associative flow rule, and then those mechanisms may be slightly larger than may occur. Generally you're going to get, but they're still going to give you an indicative place of where those where the deformations are going to happen. I've got another question about the use of Eurocode partial factors for slope stability problems. So I think the general consensus is that slope stability should be solved using design approach 1 combination 2 because basically the driving force is generally the weight of the soil in that, and you can get into all sorts of issues working out where favourable and unfavourable loads are if you use design approach 1 combination 1, and I think for those people not using design approach 1, usually design approach 3, which is very similar to design approach 1 combination 2, is the recommended one for slopes. Okay, I think in view of the time we should probably wrap up there, so I'll just pass back to my colleague Tom to wrap up for you, and thank you very much for listening.
Thanks, Colin, and thanks everyone for joining us today. So, as I said, we're now near to the end of the webinar. We do hope you found it informative. For people who are current users of the software, then we hope you learned something new about the software that maybe you didn't know before. If the webinar has prompted any questions from anybody, then please do get in touch via telephone, or you can email us on support@LimitState.com, and we'll be more than happy to answer any questions for you. For people who aren't current users of the software, then we'll be in touch over the next few days just to get some feedback, find out if you have any further questions, and see whether you think it might be useful for you. If you would like to watch a recording of this webinar, or if you think you might know somebody who would be interested to see it, then there should be one available later today or early tomorrow. There will be an email going out with a link once it's available online on our YouTube channel. Everyone here may also be interested to know that there's going to be a number of other scheduled webinars this year dealing with LimitState GEO, as well as our other software applications, and so please do look out for the event notifications that will be sent out to you or posted on our website at www.limitState.com/events. So finally, I'd just like to say, firstly, apologies for the slight delay at the beginning, but we managed it eventually, and thank you all for listening, and I do hope that you can join us again for one of the future sessions. Goodbye.